In geometry, inversive geometry is the study of those properties of figures that are preserved by a generalization of a type of transformation of the Euclidean plane, called inversion. These transformations preserve angles and map generalized circles into generalized circles, where a generalized circle means either a circle or a line. Loosely speaking, a circle with infinite radius. Many difficult problems in geometry become much more tractable when an inversion is applied. The concept of inversion can be generalized to higher dimensional spaces. Circle inversion. Inverse of a point. To invert a number in arithmetic usually means to take its reciprocal. A closely related idea in geometry is that of inverting a point in the plane. The inverse of a point P with respect to a reference circle O, with center O and radius R, is a point P, lying on the ray from O through P such that O, P, times O, P, single quote, equals R, 2. Display style op times op caret prime equals R caret 2. Closing curly bracket. This is called circle inversion or plane inversion. The inversion taking any point P, other than O, to its image P, also takes P back to P. So the result of applying the same inversion twice is the identity transformation on all the points of the plane other than O. To make inversion an involution, it is necessary to introduce a point at infinity, a single point placed on all the lines, and extend the inversion. By definition, to interchange the center O and this point at infinity, it follows from the definition that the inversion of any point inside the reference circle must lie outside it, and vice versa, with the center and the point at infinity changing positions, whilst any point on the circle is unaffected, is invariant under inversion. In summary, the nearer a point to the center, the further away its transformation, and vice versa, equals compass and straight edge construction. Point outside circle, equals, to construct the inverse P, of a point P outside a circle O. Draw the segment from O, center of circle O, to P. Let M be the midpoint of OP. Draw the circle C with center M going through P. Let N and M be the points where O and C intersect. Draw segment NN. P is where OP and NN intersect. Equals compass and straight edge construction. Point inside circle. Equals, to construct the inverse P of a point P inside a circle O. Draw ray R from O, center of circle O, through P. Draw line S through P, perpendicular to R. Let N be one of the points where O and S intersect. Draw the segment on. Draw line T through N perpendicular to on. P is where ray R and line T intersect. Dutter's construction. There is a construction of the inverse point 2A with respect to a circle P that is independent of whether A is inside or outside of P. Consider a circle P with center O and a point which may lie inside or outside of the circle P. Take the intersection point C of the ray OA with the circle P. Connect the point C with an arbitrary point B on the circle P, different from C. Reflect the ray BA in the line BC and let H be the reflection which cuts the ray OC in a point A. A is the inverse point of A with respect to circle P. Properties. The inversion of a set of points in the plane with respect to a circle is the set of inverses of these points. The following properties make circle inversion useful. A circle that passes through the center O of the reference circle inverts to a line not passing through O, but parallel to the tangent to the original circle at O, and vice versa, whereas a line passing through O is inverted into itself, but not point-wise invariant. A circle not passing through O inverts to a circle not passing through O if the circle meets the reference circle. These invariant points of intersection are also on the inverse circle. A circle, or line, is unchanged by inversion if and only if it is orthogonal to the reference circle at the points of intersection. Additional properties include: if a circle Q passes through two distinct points A and A, which are inverses with respect to a circle K, then the circles K and Q are orthogonal. If the circles K and Q are orthogonal, then a straight line passing through the center O of K and intersecting Q does so at inverse points with respect to K. Given a triangle AB in which O is the center of a circle K, and points A and B inverses of A and B with respect to K, then O, A, B equals O, B, single quote, A, single quote, and O, B, A, equals O, A, single quote, B, single quote. Display style angle AB equals angle OBA text and angle OB equals angle OAB. Closing curly bracket. The points of intersection of two circles P and Q orthogonal to a circle K are inverses with respect to K. If M and M are inverse points with respect to a circle K on two curves M and M, also inverses with respect to K, then the tangents to M and M at the points M and M are either perpendicular to the straight line MM, or form with this line an isosceles triangle with base MM. Inversion leaves the measure of angles unaltered, but reverses the orientation of oriented angles. Application: for a circle not passing through the center of inversion, the center of the circle being inverted and the center of its image under inversion are collinear with the center of the reference circle. This fact can be used to prove that the Euler line of the in-touch triangle of a triangle coincides with its Euler line. The proof roughly goes as below. Invert with respect to the incircle of triangle ABC. The medial triangle of the in-touch triangle is inverted into triangle ABC, meaning the circumcenter of the medial triangle, that is, the 9-point center of the in-touch triangle. The incenter and circumcenter of triangle ABC are collinear. Any two non-intersecting circles may be inverted into concentric circles. Then the inverse of distance, usually denoted delta, is defined as the natural logarithm of the ratio of the radii of the two concentric circles. In addition, any two non-intersecting circles may be inverted into congruent circles, using circle of inversion centered at a point on the circle of antisimilitude. The Peacholi-Lipkin linkage is a mechanical implementation of inversion in a circle. It provides an exact solution to the important problem of converting between linear and circular motion. Pole and polar equals. If point R is the inverse of point P, then the lines perpendicular to the line PR through one of the points is the polar of the other point. The poles and polars have several useful properties. If a point P lies on a line L, then the pole L of the line L lies on the polar P of point P. If a point P moves along a line L, its polar P rotates about the pole L of the line L. If two tangent lines can be drawn from a pole to the circle, then its polar passes through both tangent points. If a point lies on the circle, its polar is the tangent through this point. If a point P lies on its own polar line, then P is on the circle. Each line has exactly one pole. Inversions in 3 dimensions. Circle inversion is generalizable to sphere inversion in 3 dimensions. The inversion of a point P in 3D with respect to a reference sphere centered at a point O with radius r is a point P, such that O, P, times O, P, single quote, equals R, 2. Display style, script style op, times op caret prime, equals R caret 2. and the points P and P are on the same ray starting at O. As with the 2D version, a sphere inverts to a sphere, except that if a sphere passes through the center O of the reference sphere, then it inverts to a plane. Any plane not passing through O inverts to a sphere touching at O. A circle, that is, the intersection of a sphere with a secant plane, inverts into a circle, except that if the circle passes through O it inverts into a line. This reduces to the 2D case when the secant plane passes through O, but is a true 3D phenomenon if the secant plane does not pass through O. Examples: sphere equals. The simplest surface, besides a plane, is the sphere. The first picture shows a non-trivial inversion. The center of the sphere is not the center of inversion of a sphere together with two orthogonal intersecting pencils of circles. Cylinder, cone, torus equals. The inversion of a cylinder, cone, or torus results in a duopencyclide. Spheroid equals. A spheroid is a surface of revolution and contains a pencil of circles which is mapped onto a pencil of circles. See picture. The inverse image of a spheroid is a surface of degree 4. Hyperboloid of one sheet equals. A hyperboloid of one sheet, which is a surface of revolution, contains a pencil of circles which is mapped onto a pencil of circles. A hyperboloid of one sheet contains additional two pencils of lines, which are mapped onto pencils of circles. The picture shows one such line, blue, and its inversion. Stereographic projection is the inversion of a sphere. A stereographic projection usually projects a sphere from a point n, n, north pole, of the sphere onto the tangent plane at the opposite point s, s, south pole. This mapping can be performed by an inversion of the sphere onto its tangent plane. If the sphere, to be projected, has the equation x 2 plus y 2 plus z 2 equals minus z, display style x caret 2 plus y caret 2 plus z caret 2 equals z. Alternately written, x 2 plus y 2 plus z plus 1 2 2 equals 1 4. Display style x caret 2 plus y caret 2 plus z plus tfrac 1 2 caret 2 equals tfrac 1 4. Center 0 0 minus 0.5. Display style 00 minus 0.5. Closing curly bracket. Radius 0.5. Display style 0.5. Green in the picture. Then it will be mapped by the inversion at the unit sphere. Red onto the tangent plane at point s equals 0 0 minus 1. Display style s equals 00 minus 1. Closing curly bracket. The lines through the center of inversion, point n, display style n, are mapped onto themselves. They are the projection lines of the stereographic projection. 6 sphere coordinates. The 6 sphere coordinates are a coordinate system for three-dimensional space obtained by inverting the Cartesian coordinates. Axiomatics and generalization. One of the first to consider foundations of inversive geometry was Mario Pieri in 1911 and 1912. Edward Kasner wrote his thesis on invariant theory of the inversion group. More recently, the mathematical structure of inversive geometry has been interpreted as an incidence structure where the generalized circles are called blocks. In incidence geometry, any affine plane together with a single point at infinity forms a Mobius plane, also known as an inversive plane. The point at infinity is added to all the lines These Mobius planes can be described axiomatically and exist in both finite and infinite versions. A model for the Mobius plane that comes from the Euclidean plane is the Riemann sphere. Invariant. The cross ratio between 4 points x, y, z, w, display style x, y, z, w, is invariant under an inversion. In particular, if O is the center of the inversion and R1, display style R_1, and R2, display style R_2, are distances to the ends of a line L, then length of the line d, display style d, will become d slash r1 r2, display style d r_1 r_2, closing curly bracket, under an inversion with center O. The invariant is I equals pipe x minus y pipe w minus z pipe x minus w pipe y minus z pipe. Display style I equals frac x y w z x w y z. Relation to Erlangen program. According to Coxeter, the transformation by inversion in circle was invented by L. I. Magnus in 1831. Since then this mapping has become an avenue to higher mathematics. Through some steps of application of the circle inversion map, a student of transformation geometry soon appreciates the significance of Felix Klein's Erlangen program, an outgrowth of certain models of hyperbolic geometry. Dilations. The combination of two inversions in concentric circles results in a similarity. Homothetic transformation, or dilation, characterized by the ratio of the circle radii x, r2, x, pipe 2, equals y, t, 2, y, pipe 2, equals t, r2, x. Display style x maps to r caret 2 frac x caret 2 equals y maps to t caret 2 frac y caret 2 equals left frac t r right caret 2 x. Closing curly bracket. Reciprocation. When a point in the plane is interpreted as a complex number, z equals x plus I, y. Display style z equals x plus I, y. Closing curly bracket. With complex conjugate, z equals x minus I, y. Display style bar z equals x I, y. Then the reciprocal of z is 1. Z equals z pipe 2. Display style, script style, frac 1, z equals frac bar z caret 2. Consequently, the algebraic form of the inversion in a unit circle is given by z w. Display style z maps to w, where w equals 1, z equals 1, z. Display style w equals frac 1 bar z equals over line left frac 1 z right. Closing curly bracket. Closing curly bracket. Closing curly bracket. Reciprocation is key in transformation theory as a generator of the Mobius group. The other generators are translation and rotation, both familiar through physical manipulations in the ambient 3 space. Introduction of reciprocation, dependent upon circle inversion, is what produces the peculiar nature of Mobius geometry, which is sometimes identified with inversive geometry of the Euclidean plane. However, inversive geometry is the larger study since it includes the raw inversion in a circle, not yet made, with conjugation, into reciprocation. Inversive geometry also includes the conjugation mapping. Neither conjugation nor inversion in a circle are in the Mobius group since they are non-conformal. See below. Mobius group elements are analytic functions of the whole plane and so are necessarily conformal, transforming circles into circles. Consider, in the complex plane, the circle of radius r, displaystyle r, around the point a, displaystyle a, z, minus a, z, minus a, equals r2, displaystyle za, caret asterisk equals r caret 2, where without loss of generality, a, r, displaystyle a, in mathbar r, using the definition of inversion, w equals 1 slash z, displaystyle w equals 1 z caret asterisk. It is straightforward to show that w, displaystyle w, obeys the equation w minus a 2 minus r 2 w plus a 2 minus r 2 equals r 2 minus r 2 displaystyle w caret asterisk frac a caret 2 r caret 2, closing curly bracket w plus w caret asterisk plus frac a caret 2 r caret 2 equals frac r caret 2 a caret 2 r caret 2 showing that the w, displaystyle w, describes the circle of center a 2 minus r 2, displaystyle frac a caret 2 r caret 2, closing curly bracket, and radius r, pipe a 2 minus r 2, pipe, displaystyle frac r a caret 2 r caret 2. When a r, displaystyle a right arrow r, the circle transforms into the line parallel to the imaginary axis w plus w equals 1 slash a, displaystyle w plus w caret asterisk equals 1 a. Higher geometry, as mentioned above, 0. The origin requires special consideration in this circle inversion mapping. The approach is to adjoin a point at infinity designated infinity 1 over 0. In the complex number approach, where reciprocation is the apparent operation, this procedure leads to the complex projective line, often called the Riemann sphere. It was subspaces and subgroups of this space and group of mappings that were applied to produce early models of hyperbolic geometry by Beltrami, Cayley, and Klein. Thus, inversive geometry includes the ideas originated by Lobachevsky and Bolyai in the plane geometry. Furthermore, Felix Klein was so overcome by this facility of mappings to identify geometrical phenomena that he delivered a manifesto, the Erlangen program, in 1872. Since then, many mathematicians reserve the term geometry for a space together with a group of mappings of that space. The significant properties of figures in the geometry are those that are invariant under this group. For example, Smogajewski developed several theorems of inversive geometry before beginning Lobachevskian geometry. Inversion in higher dimensions. In n-dimensional space where there is a sphere of radius r, inversion in the sphere is given by x I r 2 x I j 2 display style x underscore I mapsto frac r caret 2 x underscore I sum underscore j x underscore j caret 2. The transformation by inversion in hyperplanes or hyperspheres in N can be used to generate dilations, translations, or rotations. Indeed, two concentric hyperspheres, used to produce successive inversions, result in a dilation or contraction on the hypersphere's center. Such a mapping is called a similarity. When two parallel hyperplanes are used to produce successive reflections, the result is a translation. When two hyperplanes intersect in an N2 flat, successive reflections produce a rotation where every point of the N2 flat is a fixed point of each reflection and thus of the composition. All of these are conformal maps, and in fact, where the space has three or more dimensions, the mappings generated by inversion are the only conformal mappings. Liouville's theorem is a classical theorem of conformal geometry. The addition of a point at infinity to the space obviates the distinction between hyperplane and hypersphere. Higher dimensional inversive geometry is frequently studied then in the presumed context of an N-sphere as the base space. The transformations of inversive geometry are often referred to as Mobius transformations. Inversive geometry has been applied to the study of colorings, or partitionings, of an N-sphere. Anticonformal mapping property. The circle inversion map is anticonformal, which means that at every point it preserves angles and reverses orientation. A map is called conformal if it preserves oriented angles. Algebraically, a map is anticonformal if at every point the Jacobian is a scalar times an orthogonal matrix with negative determinant. In two dimensions, the Jacobian must be a scalar times a reflection at every point. This means that if J is the Jacobian, then J T equals K I display style script style J C dot J caret T equals key, and det J equals minus K display style script style det J equals sqrt K closing curly bracket. Computing the Jacobian in the case C equals she x2, where x2 equals x12 plus xn2 gives jt equals key, with k equals 1 x4, and additionally det j is negative. Hence the inversive map is anticonformal. In the complex plane, the most obvious circle inversion map, i.e., using the unit circle centered at the origin, is the complex conjugate of the complex inverse map taking z to 1, z. The complex analytic inverse map is conformal and its conjugate, circle inversion, is anticonformal. In this case, a homography is conformal while an antihomography is anticonformal. Inversive geometry and hyperbolic geometry. The n-1 sphere with equation x 1 2 plus x n 2 plus 2 a 1 x 1 plus 2 a n x n plus c equals 0. Display style x underscore 1 caret 2 plus c dots plus x underscore n caret 2 plus 2a underscore 1 x underscore 1 plus c dots plus 2a underscore n x underscore n plus c equals 0. Will have a positive radius if a12 plus and 2 is greater than c. And on inversion gives the sphere x 1 2 plus x n 2 plus 2 a 1 c x 1 plus 2 a n c x n plus 1 c equals 0. Display style x underscore 1 caret 2 plus c dots plus x underscore n caret 2 plus 2 frac a underscore 1 c x underscore 1 plus c dots plus 2 frac a underscore n c x underscore n plus frac 1 c equals 0. Closing curly bracket. Hence, it will be invariant under inversion if and only if c equals 1. But this is the condition of being orthogonal to the unit sphere. Hence we are led to consider the n-1 spheres with equation x 1 2 plus x n 2 plus 2 a 1 x 1 plus 2 a n x n plus 1 equals 0. Display style x underscore 1 caret 2 plus c dots plus x underscore n caret 2 plus 2a underscore 1 x underscore 1 plus c dots plus 2a underscore n x underscore n plus 1 equals 0. Closing curly bracket. Which are invariant under inversion, orthogonal to the unit sphere, and have centers outside of the sphere. These, together with the subspace hyperplanes separating hemispheres, are the hypersurfaces of the Poincare disk model of hyperbolic geometry. Since inversion in the unit sphere leaves the spheres orthogonal to it invariant, the inversion maps the points inside the unit sphere to the outside and vice versa. This is therefore true in general of orthogonal spheres, and in particular inversion in one of the spheres orthogonal to the unit sphere maps the unit sphere to itself. It also maps the interior of the unit sphere to itself, with points outside the orthogonal sphere mapping inside, and vice versa. This defines the reflections of the Poincare disk model if we also include with them the reflections through the diameters separating hemispheres of the unit sphere. These reflections generate the group of isometries of the model, which tells us that the isometries are conformal. Hence, the angle between two curves in the model is the same as the angle between two curves in the hyperbolic space. See also circle of antisimilitude, duality, projective geometry, inverse curve, limiting point, geometry, Mobius transformation, projective geometry, Soddy's-Hexlet, inversion of curves and surfaces. German. Notes. Altschuler Court. Nathan. 1925. College Geometry. An Introduction to the Modern Geometry of the Triangle and the Circle. 2nd ed. New York. Barnes & Noble. LCCN 52-13504. Blair, David E. 2000. Inversion Theory and Conformal Mapping. American Mathematical Society. ISBN 0-8218-2636-0. Brannan, David A. Esplin, Matthew F. Gray, Jeremy J. 1998. Chapter 5. Inversive Geometry. Geometry. Cambridge. Cambridge University Press. pp. 199-260. ISBN 0-521-59787-0. Coxeter, H. S. M. 1969. 1961. Introduction to Geometry. 2nd ed. John Wiley & Sons. ISBN 0-471-18283-4. Hartshorne, Robin. 2000. Chapter 7. Non-Euclidean Geometry. Section 37. Circular Inversion. Geometry. Euclid and Beyond. Springer. ISBN 0-387-98650-2. K. David C. 1969. College Geometry. New York. Holt, Reinhardt and Winston. LCCN 69120075. Inversion. Reflection in a circle at Cut the Knot. Wilson Stothers Inversive Geometry page. IMO Compendium Training Materials Practice Problems on how to use inversion for Math Olympiad. Problems. Weinstein, Eric W. Inversion. Math World. Visual Dictionary of Special Plane Curves XAH Lee.